This lecture is being brought to you in partnership with the University of West Florida.
Okay, I'm on. I'm live. Every which way. Okay, great. So it's a pleasure to be here. When I told my daughters I was going to do the smart lecture down here, they said, "Dad, you're not that smart." It's good. My children have kept me grounded very, very nicely. But anyway, it's been a pleasure. I really had a good time at the university this morning, and happy to be here and saw some amazing things across the street and behind here with the robotics and things that are going on at this institute. So today I'm going to tell you about a subject, and we work a lot of different things in my group over the time, but everything almost always comes back to how do you make a sensor? How do you make a sensor? I have a colleague used to say, "Tim, you look at anything, you see a sensor, a way to sense things." And so this is going to be telling you about what we do to try and come up with chemical sensors, although we've done, optical, radiological, you name it, we've done this kind of a sensor. But I'm going to focus on chemical sensors today. And the first thing, maybe to kind of motivate this, why would we care about chemical sensors? And if you have your water analyzed, or you're looking for things, more likely the samples are being sent to an analytical lab. Looks like this, that has equipment like I saw across the street. That's every one of these pieces is hundreds of thousands of dollars and takes a trained, dedicated staff member to operate it and to maintain it. And this is how you typically analyze chemical content on things. Now, chemical sensors this is kind of just a collection of things that they look like. They can look very, very simple. They can be much less expensive. They can be battery operated. I'll show you examples of that. Or sometimes even not even have a battery, be operated wirelessly. Your smartphone can power a sensor, so I'll show you. They can give you distributed information. If you want to know, the atmosphere around and have attribution to who's polluting, that's great. Or you just want to know, is the atmosphere in this room of my house better than that? Having a chemical sensor can tell you that. And ideally, they're going to be things that you could use, that anybody could use. You don't have to be a trained technician to use these materials. Now, there are limits, however, to sensors. Now, what I'm going to tell you about today is how you can enhance sensors through kind of a materials development, how you make things that we call them transducers, things that actually respond to what you're looking for and give you a signal that is really easy to detect, something that's strong and easy to detect that can make for simple, so you don't have to have some big piece of equipment. A problem, however, is when we do the things I'm going to show you about is that they aren't perfect, right? There's going to be something, selectivity, or we might call cross-reactivity, okay? That is even in nature, we think of nature as being really, our bodies as being so selective. The only thing that's really that selective is DNA, RNA, duplex formation. Everything else is like all over the place, and there's complex systems that are regulating that, but cross-reactivity is really important. And in fact, that's led to a lot of sensors being thought about in terms of what we call the e-nose concept. And for example, your nose, we have receptors, and they respond to certain things more than others. They respond to things that are things that are stinky, often are associated with rotten food, right? It's good to be able to smell something and know that you shouldn't eat it, right? And that's usually something the elements that do that. They're sulfur, often, or alkenes, and they interact with other particular things that our noses have receptors that do these things. But also, even though you might recognize a smell, you can't quantify things, right? So your nose is kind of, it's detecting a lot of different things at the same time. You don't know how much of what, so it's really tricky. But this is something that people really try and emulate in these. Another thing that's a little tricky with these sensors is they're prone to drift into aging. I constantly get people say, I want to put a sensor out. I want it to work for a year without anybody touching it. And I said, well, and I want it to take no power. And I said, well, that's kind of tricky. I said, you go not take a bath for a year, you're going to have, you're not going to be so good. You're not going to be as clean. Things stick to sensors and things. So that you have to have them expose the environment. So there are tricky things like that. But ideally, they can be inexpensive. And that idea of that you don't have to last a year, they can be consumables. And if you do that, you want to make things that you can throw away, obviously, and not have this. Now, so today, one of the themes I'm going to tell you about is how we use different, what I would call synthetic conductors, or I'm going to talk here about what we call electronic polymers. So polymers are things where you take a unit and you stitch them together. That's what this N means, is we had many of them. And what's really important about these polymers right here, and it's been interesting to us, is that they have really big ranges of conductivity and they're really sensitive. So electrical conductivity is one of those properties that spans many orders of magnitude, much more than we think about in terms of space, in terms of going around the world or anything like that. But it's not unusual to have things that have 13 orders of magnitude difference in their electrical conductivity, depending on their physical state. So these polymers can have these big ranges of conductivity, and they can change very dramatically with what we call doping levels. And I'm going to tell you a little bit about that also. Okay, so the simplest polymer up here, as you might expect, is this one. It's called polyacetylene. This is kind of what a section of that polymer looks like. And it was shown back in 1977 that you could make versions of this that were about as conductive as aluminum metal. And we use aluminum in a lot of our wiring. I mean, copper is better, but it's more expensive. But aluminum is in a lot of the wiring you might use around a building, even like this. And these three gentlemen won the Nobel Prize. I had the pleasure of being a colleague with Al McDermott as an assistant professor. They showed that this can become conductive. Now, it turns out this material, polyacetylene, though, is not intrinsically conductive. It doesn't conduct electricity by itself. If I have it really clean and it's just pure, it's actually kind of insulating. It's not a very good conductor. And that's because what we find here is you have something called an energy gap that I'm going to tell you about. So when you have this polymer here, every time you see these are carbon atoms here, and there are, maybe best to show on the last slide, you see these are carbon atoms, those are hydrogens, these are double bonds. And in organic shorthand, I realize we kind of leave out some of the things here. We don't put the carbons in, and we don't all the hydrogens. It's just a shorthand. But for every one of these double bonds, there's a pair of electrons. And as this gets longer and longer, we get more and more pairs of electrons. And eventually you get, and this gets really long, and you put a bunch of them together, you think of them as forming essentially a continuum of different orbital states. Think of this like a vessel that I poured and I filled it up with electrons, right? And they're all there in this. And they have different bonding characteristics. And then this is another essentially vessel that has orbitals, which electrons live in orbitals, but it's empty. Okay, but this is completely full, and there's some reasons why there's this band gap. It has to do with different bond lengths, and this interaction between two of them, the same sign is good, this is bad. When this is short, when this is long, that minimizes that. When it's shorter, it makes it higher. There's a few things that cause this band gap. But when you make this structure, it's really insulating. And the analogy to understand this is a parking lot. And so if I have this parking lot right here, and I want to move, I can't move these cars. They can go back and forth a little bit, but you cannot move one of these cars over big distances, right? It's packed in there. But if I take a bunch of the cars out, now I can start moving them, okay? And so this is a thing that when you have completely full, the little vessel, we call it an energy band, when they're completely full of electrons, or they will not conduct, or completely empty. If there's no electrons there, there's nothing to move. Electrons are the things that are going through these circuits here. And so this is a concept. In order to make it so you can move these, if you think of these cars as electrons, you have to take some of them out. And so this is what they got the Nobel Prize for, is they figured out, they took this polymer and they took a bunch of electrons out. And this is the state that's really conductive that looks like aluminum. And so what we did is we took a bunch of these electrons out, and now I'm drawing them as positive charges here, because when you take the electron is satisfying the charge on the carbon, and when I take electron away, electrons are negatively charged, I leave behind a positive charge here. So this is what we also call doping, okay? And doping is something that comes from semiconductors, silicon. It's a term that's used widely that way. Okay, so we do this, we put these charges in there, but let's go back to the kind of molecular world, and we think about how do these charges move. Well, it turns out the charges, the electrons move, but it looks like the hole's moving. So the electrons, the way chemists think about electrons, we keep track of them, right? So every time there's this two bonds together, we know there's an extra pair of electrons, and we use these curved arrows so we don't lose track of them. And this is actually something we just do just routinely in chemistry. And so what I can see here is I can move this positive charge from there to there. This positive charge, we're going to call this a hole, because that's where an electron was taken away. It left an empty site or a hole behind it. And so you can look at this, you can think of this as like this hole is moving, but really the electrons are moving over there. But we often think of it as hole conduction right here. The same thing with a more elaborated polymer here. We tend to put the positive charges on things like atoms other than carbon, because they're more stable that way. But this is, again, a curved arrow where I move this charge to there, that charge to there. And this is a case where they're moving together. We call it a bipolaron. We call this a soliton. There's some semiconductor physics terms there, but that's what we have. So this is kind of some basics of kind of synthetic conductors and how to think about them, and I'll come back to that more. But I want to tell you, something about my sensing experience, and it began a long time ago. When I was a graduate student, my inspiration came from reading this paper in the literature. And so in this case, they took the polyacetylene I'm telling you about. Instead of taking electrons out of it, they put an extra one in it. So electron's negative charged. If I add an extra electron, now it's a negatively charged. That electron can't exist without its complementary cation. Otherwise, things just become really, really charged, and they eventually kind of explode because all the electrons will repel each other. So you have to have a charge with it. In this case, it was sodium. And so what they found that is they could take this, they could put these charges in there, but then if they expose this to a salt, and the electron can't really move very well because it likes to be next to its cation. There's strong electrostatic forces there. And now if you expose this to THF vapor, it solvates this and moves it away. And by moving this further away, it releases this electron, and now it can move. And this changes its conductivity by a factor of 10 to the 4. Just with a little whiff of solvent. THF this is a very standard solvent that chemists use. So I saw that, and that was kind of interesting. And then when I was a graduate student, this is a polymer called polyaniline, and it's got these charges, and these are two different forms where the charges can be kind of one step away, and this has a radical associated with this. This one doesn't. But this is part of the conduction process in this. But I decided I wanted to play with this polymer, so I made some of it. And then I did something. We use these apparatus, we call them glove boxes in chemistry, and there are ways of doing air-sensitive chemistry, but there's no moisture or no air. And I took it inside a glove box, and I found that it did not conduct electricity at all. And I took it back out in the air, and I put a little multimeter on it, and I said, no, it conducts. And the problem is, when I got rid of all the water, these chlorides got too close to there. When there's water around, chloride is really soluble in water. That's why sodium chloride dissolves so well in water. Like water likes the sodium, it also likes the chlorides. And the water basically removes the chlorides, And so this came to me as like, hey, you know, there's some really cool, this kind of interactions between charges and carriers. Maybe I can use this to make chemical sensors or do things. And then also these materials are really sensitive. So I came up with a very ostentatious, I mean, just an idea that it's still more of a concept and it's something to motivate the way I think than something that's a reality. And I said, okay, I want to make the best sensor, or the most sensitive sensor ever. And what I'm going to do is I'm going to take and I'm going to make a molecular wire, and I'm going to put it between two electrodes so I can measure just, it's a circuit, I can measure the resistance, the resistivity through this. So I can measure how easy the electrons flow. And I'm going to put charges in them, because remember, I have to have the half-full parking lot to get things to go through this. I got charges through them, and on every one of these little repeating elements in my molecular wire, I'm going to put something that I'm going to call a receptor. This is something that is designed to bind something else. And so, this one is a receptor for little red balls, right? This is going to bind a little red ball. And when the red ball binds this, it's going to create a barrier for this to move through this. And so what can happen here is only one of these needs to be activated to block, because this is like something that it can't go over. Just think of it as a barrier. It's an energy barrier. So this comes up and it hits that wall and it can't go through it. And if I have millions of these in a row, only 1 out of a million has to be occupied, and boom, it shuts off. So just think of it like, you know, we don't have to deal with this anymore, but growing up, trying to get your holiday lights on your thing, and you have one light bulb burned out, nothing works, right? Just one. And I still have some of those things. I'm going to throw them all away eventually, but because every year they confound me. Okay, so we went on this, and we started thinking about how do we create these barriers, and here's kind of now showing you kind of chemistry-wise types of things we would do. We would take, this is a case where we made a barrier for something called paraquat, which is a nasty herbicide. And this is a little hoop here that like this, and when paraquat fits in there, it has 2 positive charges. The hole, remember, we're thinking of these as holes is moving, is positive charge. It runs into this. It doesn't like these other positive charges, and that creates a barrier. Or here, what we did is we made something for fluoride ion, where what we did, we have these polymers here that we have a receptor that binds fluoride ions, and when you get them in there, the fluoride likes the hole, negative likes positive. Rather, this case it's repulsive, this case it's attractive, and it captures them and it snags them so they can't move anymore. Okay, so we've done these different things. Okay, but you know, we still keep wanting to come back to this scheme, and the reasons that this isn't so easy is, one is like it is not easy to make a molecule have a really stable, a single molecule, just like one carbon atom here, have a really stable electrical junction with an electrode. That is just really hard. And then also, there's something called the second law of thermodynamics, which says that nature always tends to disorder. We know this, that if you take, you know, if you have, you know, you don't constantly keep straightening up your house, it tends to higher degrees of disorder. It's fundamental in everything that we do. And this molecule doesn't want to stay stranded up like this. It's trying to figure out how to get away and how to disorder. And so there are problems with that. And so there are so many things. So I was constantly looking for new things to do. And in the late 90s, a solution came about. And it was carbon nanotubes. So carbon nanotubes are things that look something like this. These are kind of arrays of carbons. And some of them are metallic, some of them are not. Some of them look more like the polyacetylene I showed you, which you call a semiconductor, that have to be doped. We tend to look with the semiconductor ones. And you describe them as having, you know, if you cut segments and roll them up. So if I cut normal to this vector here, and I roll that up, that would be 1 nanotube, and I could roll them up this way too. So just think of these are cigars. I could slice through this, connect that to that side, make one type. I could cut at this angle, that. And so there's a whole zoo of these different ones. And just to kind of show you how that rolling up does, here's one where they're just showing how, you know, you have a a bunch of this, and they're not made this way, but this is how you can think of them, right? And you can see how this looks like graphite, like a single sheet of graphite we call graphene. So anyway, these little things were really challenging to work with initially, and part of it is they had the solubility of brick dust, right? They just did not want to dissolve. And it's because they like each other so much. Their electrons, they just pack in this nice little, all these nice little these little cylinders, and they do not want to dissolve. And so we first started in this area, and took me a while. Actually, my first student that I got on this project, he told me after about 6 months, I can't deal with these things. They won't dissolve. I don't know what I have. If you keep making me do this, I'm going to quit. And so I said, okay. And then I finally got somebody else in this. So that was there. So it's actually a little thing. This is what happens when you have projects like this in your research group. You wait until everybody who remembers the problems with that project has graduated. And then you offer it to somebody else as a brand new idea. This is not a joke. I do this all the time. This is a recurring theme with me. But we finally got on base here with this, and he took this polymer. So this has these double bonds in it again. That's electrons that kind of do this, and that makes it really like the nanotube. So what you do is you take these things and you activate them with an ultrasonic blast, and you kind of blast them apart. When you blast them apart, it's a little bit like a rodeo, wrapping things up with a rope here, and they wrap around here, and you get these coronas that keep them in solution. And we found that we could keep them in solution for years this way. And so we have these nanotubes, and so it's still a little bit tricky to put one nanotube between my two electrodes. But what we're going to do is we're going to say, well, we don't have one, but we have, a limited number of nanotubes. So we're going to have these interconnected pathways where you think about electrons going through the nanotubes. Between these, it might go this way and then over here. But we can make these really simple sensors that have just two electrical junctions between them. And we make things, these are what devices look like in my group. They're really simple. We just measure resistances. But the dream is to get the electrical engineers to basically translate this to this. And we still have problems, but one of the things these can be really sensitive, and they're electrical, so they fit in anywhere. And I want to show you that their power requirements are super, super low. I'm going to show you that here in a bit. So how do you go about, thinking about these? Well, analyte is the molecule we're looking for chemically. That's what we're trying to determine. And there are 3 places you have to worry about what happens at the electrode surfaces. We've kind of had that solved where it doesn't really matter. But then you're going to do things that where the analyte interacts with the nanotube itself. It can change the electronic properties of the nanotube, or it might do something at this little junction here. So the nanotubes come together, they're there, but the electrons have to jump from one nanotube to the next. And sometimes that jump is tricky, and it's kind of like trying to jump a stream, right? If you get them too far apart, then it's really hard to jump, and they might not make it. They might not be able to do it. It's called electron tunneling that happens between those two. So we've done different ones. Let me first tell you about one that we made here just really quickly that had to do with this tunneling interaction. And what we did is we used the same kind of polymer we used to disperse these things before, and we put this is like a little bucket. Think of it as like a little bucket. And what it binds is these different xylenes. Xylenes are aromatic compounds. They're in gasoline and kerosene. They're things that are in the environment that we care about. And so what we did is we showed that we could determine these all have about the same boiling point. They're very similar compounds. They just differ by a little bit of their topology and their structure. But we showed we could get different essentially resistance changes with them. So what I'm showing here is essentially the amount of current flowing through this. It's been kind of standardized, it's normalized. But the amount of current flowing through here, when you give it a little blast of one of these vapors and then you turn it off and then it goes back down. You give it a little blast, it backs down. And so this is negative. So the current is lowering So it's becoming more resistive because what's happening here is this bucket is collecting these things, and then over here between the nanotubes here, this little corona is getting fatter, and it pulls the nanotubes apart, and the electrons can't get between the nanotubes as easily. So this is that swelling mechanism, and we found that we could get differences between these that we expected based on what we understood about the chemistry. Now, carbon monoxide is a nasty compound. Turns out carbon monoxide does not interact at all with nanotubes. It doesn't have any interest with nanotubes. It doesn't bind them. But we're looking at a way to make carbon monoxide interact with nanotubes. And here's a thing from the kind of organometallic literature. Organometallic literature means you have structures that bind metals to different carbon frameworks. And here's a molecule, and this molecule went back and forth, and this nitrogen kind of pops off it, and carbon monoxide kind of takes its place. Okay, so this is what we call a substitution reaction. And without carbon monoxide, it really lives over here. But every time this pops off, even for a little bit, if carbon monoxide takes its place, it gets stuck over here. And when it gets stuck over here, this nitrogen has what's called a lone pair, and that lone pair loves positive charges. So the nanotubes now they have these positive charges in them because oxygen essentially extracts electrons, molecular oxygen in the air, extracts electrons, and when you have this, it basically pounces on it and it captures it and it stops it. And so you can do this and you get things that we put this in a fluorocarbon solvent to put it, or a chlorofluorocarbon solvent to basically get rid of a humidity effect. But we just dissolve this in it, and then whambo, we get this response. And you can see it only responds to carbon monoxide, nothing else. So very, very selective because we could use it with the chemistry. Let's give another gas here. I'm going to talk about explosives, but I've done a lot in explosives and chemical warfare. And my wife years ago was saying, like, why can't you do something nicer than that? And so I decided I got to get into food. I'm going to get into food. So it turns out ethylene is a gas. It's just two carbons with a double bond in between it, and it is the universal plant hormone. It's like it was what triggers ripening of fruit. You've all heard this as saying it takes one bad apple, right? It really just takes one bad apple. One rotten apple in a group will cause all of them to rot. And so this is something that's very important for agriculture to make sure, can we detect it? When is it getting too high? If you have a storage room, you've got a problem if you have an ethylene spike. And we made some sensors for this, and this is just showing kind of a plot of a pear giving off. But when fruit ripens, it gives off ethylene. Ethylene causes all of its neighbors to ripen faster. It does something called upregulates the enzymes that make more ethylene, and everything just goes away. But what we did is we commercialized this some years ago for apple cold storage rooms, a sensor for detecting ethylene, and also this is an inhibitor, something that would cause it to not ripen. But we did this in cold storage rooms for apples. If you eat an apple in July, it wasn't, I used to think they came from South America or something like that. No, it was picked in North America in September the year before, and it was held at low temperature in an oxygen depleted cold storage room that they basically have made sure none of the apples, they kind of arrested the apples by cooling them, and none of the apples could be putting off ethylene or everything would go bad. And what these guys wanted to do is they wanted to know if it was going bad, that room, everything's going into applesauce. They would just empty the room and make applesauce or apple cider. They wouldn't wait to open it and find them all rotten a year later, right? Okay, so apples were one thing, but I was still kind of motivated, like, do something nice, and I finally decided, let's go for flowers. Okay, so the most sensitive plants to ethylene are flowers. And flower ripening is really sensitive. So if you have, if you want your flowers to ripen, go put a banana next to them really quick. If you want them to bloom fast, do that, right? So if you buy flowers and you want them to bloom, they do that. But this is now, with that other fruit, it was part per million, or 1 in a million of the gas molecules. Here we have to get down to part per billion. And we did that. And we did that using kind of some organometallic reaction tricks here. So we just basically put a catalytic mixture of some palladium. This is ethylene, the double bond here. And we made use of a reaction called the Vaca reaction that adds essentially water across this. So, and when you do this, this is palladium that's palladium-2 that doesn't have any interest in the nanotubes. But when you do this, you make palladium that has more electrons around it. And this palladium is able to reduce the nanotubes. So what happens here is we have these nanotubes that are, again, they have these holes in them. They're hole conductors. They're conductive. And when this palladium is generated because of ethylene, the palladium fills these holes up and it says, no, you're not a conductor. You're an insulator again. I filled you up. The parking lot's full. All the electrons are filled. So the conductivity goes down. And then eventually the oxygen comes, kind of wins because you have oxygen around. It comes back and it resets it. Okay? So the oxygen starts pulling electrons out of the nanotubes again and gets you back. So we were able to do part per billion things for ethylene for food. Okay. So, is there anybody in this room that doesn't have a smartphone? No, unlikely, right? Not in the United States, anyway. So we constantly are thinking about what do we do with smartphones and how do we keep everything connected? And your smartphone is really great. I mean, traffic patterns. Yeah, we can't live without that, right? To avoid the traffic jams, to know how many steps you have, different things like that. But it would be great if your smartphones or some other sort of kind of wireless communication could give you information about your environment, chemical information, digital chemical information. Okay, so we've been interested in that, and we came up with an idea of to take devices that look like this. And this might look like a kind of anti-theft tag you find, or fact is in Europe, in really fancy cheeses, you'll find these things. And this is called a radio frequency identification card. And they make these are really cheap. They're aluminum. They're printed out on plastic. You come in big rolls and you slice them off with scissors, right? And this is a Texas Instruments one. And so what we have here, this racetrack around the outside, is an antenna. This is a capacitor to tune the circuit. And this is an integrated circuit that talks to you. So this integrated circuit right now just gives a serial number. So when the reason people might put these in fancy cheeses is you can bleep it and the serial number will tell you exactly the day it was born, right? It comes from serialization. That's what a lot of these things are used for. But we thought, could we take these kind of off the shelf, they cost about 5 cents, tags, and create them into chemical sensors? And so the way we started doing this, the first thing was we got essentially a hole punch, and we just punched out that section of there, and then we redo it with nanotubes. We put nanotubes in there, and we have to. These are the circuits here. This one's showing it open, and this is putting our material in there. That's the dynamic as our nanotubes, and your smartphone will power this. Okay, this does not have a battery on it. There's no power on this. The way that you do this is a smartphone. Your smartphone puts out 13.56 megahertz radio waves, and it does it through kind of digital pulses, and it'll say, hey, you, wake up, I'm asking you who you are, and the tag talks back to it, says, I'm RFID tag 1234. That's what happens. But all wirelessly within about 5 centimeters of each other. Every smartphone in this room will do this. And so we decided, well, this is kind of cool. Let's use this to now make a sensor that has some sort of kind of threshold thing, just binary. Am I on or am I off? Okay? If that nanotube is conductive enough, it doesn't know that it's been hurt. If the nanotube is not conductive enough, it knows that the circuit's broken, right? So it's either going to be unreadable or readable. And this sounds like kind of a silly sensor. It's just a threshold detection. But I hope to show you there's some ways that this can be useful. And the first one, I'm going to show you just a video that one of my students made in the lab. And this is a demo of, a bomb-in-the-box video.
On the left, we have an unmodified control tag. This tag will always be readable. On the right, we have a sensor tag. This tag will only turn on in the presence of an explosive. Notice how the phone does not read the sensor tag when the box is empty. Now I will place an improvised explosive mimic into the box. This mimic is chemically equivalent to many common explosives. Again, scanning the control tag indicates the system is functioning properly. Now, with the explosive material in the box, the sensor has turned on, and we see the message verifying that an explosive material has been detected. This information could automatically be relayed to the authorities.
Okay, so you can see how that could be very useful for your thing. That was a peroxide-based explosive mimic. Probably could have been explosive itself, but hopefully nobody got hurt. I was kind of a little bigger than I thought he was going to do when he showed me that, but anyway, so that's cool. But again, food. I'm trying to do, that's explosives. I went back to the dark side again. But let's do food, and let's think about something called modified atmosphere packaging. So when you buy things in the grocery store, you'll find them in packages now, a lot of the time. And you might think that's just the way the grocery store figures out how to charge you more, but actually not. It's actually a way to increase the lifetime of the produce. That is modified atmosphere. They deplete the oxygen in these things, but if they get a pinhole, the oxygen gets in and then it will spoil faster, right? So wouldn't it be great if you could put a sensor inside this packaging? Doesn't even have to be line of sight. You don't have to see it. That would tell you if oxygen went into that packaging. And so that's what we did here. We used a little bit different design of our RFID, but we put our nanotubes in it. And here we used something where we took up the nanotubes and we wrapped them with a polymer, polyphenol 4-vinyl pyridine, and we put iron ions on them. So iron in a reduced state. So iron in our blood, when we bind oxygen is in a reduced state, our body has to continually make that in that reduced state. It will oxidize in air otherwise. But this is iron in that reduced state, which is fundamentally sensitive to air. And when it gets oxidized by air, it changes it. So the idea here is, again, with my doping concept that whoops, I went backwards here. Okay, so when the iron is a really good reducing agent. So it's dumping electrons into this, and it fills up that. This is the nanotube that ordinarily would be doped or have holes in it. The nanotube, the iron 2 fills them up. So we assemble this all under inert atmosphere, under nitrogen, and then if any oxygen's around, it starts oxidizing the iron 2 to iron 3. We get some of these iron 3s. And the iron 3 takes electrons out of it and creates holes, and it becomes conducting. And so this is a way that we use to take our nanotubes and make them really sensitive to oxygen. And then you can decide how you design this so you can hit thresholds where, this is okay down here, that's not okay. Don't buy that package. So this is a way you can do food packaging. And in this paper, if you're interested, we've done it for broccoli and green tea. My student said there is nothing more important than green tea. And I told him it worked really well for green tea. And I said, yeah, but you chose the easiest thing because it's dry. So humidity can be a big problem. So I made him do broccoli with that. Do something healthy. I like broccoli. Okay. So let's come back to, again, this kind of crazy idea I had as a graduate student. In this last portion, I wanted to show you that we did this. And I started this, again, I conceived of this back when I was like a second-year graduate student. And I was showing this around when I was an assistant professor, and I got grief. Everybody's saying, like, you don't know what amplification is. I used to put the Webster's dictionary thing on it. And you don't know it's doing this. This is crazy. You don't know the molecular wires amplify. And so I decided I had to do experiments that proved my wires would amplify. But I couldn't connect them to electrode. I didn't know how to put one between an electrode. I didn't know how to do this. And then also, if you're doing only one molecule at a time, you got really crazy statistics. I mean, everything's different. and everything's going to be very complicated. So what I want to do is I want to measure millions of them at once and get an average number and see that it really works. And the way I decided to do this is to do it a different way, to do it with light. So now, let's think about a solution of my wires here. This is my wire. I have a whole bunch of these in a solvent. Now, these wires are now, they're not conducting. They have their filled band here. Now I'm showing it also in a spatial dimension along this, and they have an empty one, okay? But these wires, I have them in solution, but if I excite them with light here, what I do is the light, when it's absorbed by this, it takes an electron from this spate and it kicks it up in energy. The energy has to go somewhere. The electron has to jump up there. And when it jumps up, these two can zoom along this back. It's like a superhighway. They go really fast. And then if they find my little receptors that have either red, yellow, or green balls, they can do different types of reactions. They can do, this one is where the electron would jump over to the red ball and then jump back. That's what I'm showing here. This one is where the electron from here would go the other way, and then that would backfill. And I'll show you this example of this, and I'll show you something like this where the hole, like a balloon, will kind of get up because the electrons are filling behind it. So the hole's really like a balloon. It's empty. Just go exactly like a balloon. And the electron is going to fall down into this pit. And this is now at a lower energy. So this vertical axis is energy. And in light, that means it goes to longer wavelengths or goes from like blue to red, or blue to green in this case. Okay, so we first went on to demonstrate this works, and this is getting a little technical, but hopefully you can follow along here. What we did is we took a single molecule and we measure how strongly this molecule binds. And this is like something that when this is ordinarily a really bright fluorescent molecule, if you put light on it, it glows. And when you add these things to it, it kills the fluorescence. It does something called quenching. And we did this, and we can measure what we call the equilibrium constant, how strong this is. And then we took a polymer, where we hooked a whole bunch of these together, and we did the same experiment, and we found that it was much larger. Okay? And that's because what happens is when that light hits it, it can go boop, 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 nobody home, nobody home, nobody home, nobody home, oh, boom, bam, I'm dead, right? So you could get this amplification along this wire. Now, so we got 140 units that this could run around long, and I was excited about that, but it's still 140, I wanted more, thousands, millions, whatever. And I'm going to get off stage for this but what I didn't realize, I was so enamored with my molecular wire between two electrodes, and I was just thinking that like everything's going to go like this in one direction. But when you put a photon in here, there's nothing telling this which way to go. It's like putting your car in forward and reverse randomly, okay? And for me to go in random steps like this, for me to go 140 linear steps, which it was doing, it had to take 140 squared, or 20,000 steps. So this is like horribly inefficient. I'm wearing a place in the carpet here, right? It's just going back and forth over the same place over and over and over again. And so it just took me like 6 months to realize this. It's kind of crazy how long it took me. But the answer is like I was so obsessed with the single wires in solution demonstrating the amplification that all you had to do was just take a little wind out of my sails. Let's just go back to solid things and not worry about single wires, and show that when we get something like this, we get an excited state and it can run around. And when it's free to run like that, it can get close to those 20,000 steps, right? Maybe not perfectly, but it can get to that. And it will have a much higher chance, and statistically it has a better chance of finding that kind of chance molecule that we're looking for. And so we made these molecules which have kind of intrinsic porosity. They're very durable. And we demonstrated this with the detection of the explosive TNT. So TNT is an explosive it's the cheapest explosive. It's very safe. It doesn't. You have to detonate it with a blasting cap usually. It's easy to handle in the lab, but it is dirt cheap to make, and it's a very powerful explosive, but it's not very volatile. Okay, so we initially got started with landmine detection with this, and so what TNT does is it sticks to the polymer here, and then when these excited states that you generate go zooming up and down. If they find the TNT, the electron jumps over to the TNT and then jumps back and it kills it. So it quenches the fluorescence goes down. So what I'm showing here is data from a device I'm going to show you just in a moment, where it's looking, there's a tech who's out at a site where we had a bunch of explosives that were, when you have what we call demolition packs, are usually wrapped up nicely in plastic. So it isn't just like explosives all over the place. And he went 2 meters, figured out which way was downwind. And what he's doing is being very patient, standing there, and all at once, he starts getting these like signals. Now, you might say this looks kind of weird data, but this is what we call a filamentary pattern. So if I was up here, like in the old days, I got shown the ashtrays in your building today. But if I was smoking a cigarette while giving this lecture, right, at the base of the cigarette, you would see a little filament, but then it would diffuse, right? So that part is where it's convecting and then it's diffusing. So we're in the convection part of this before it diffuses. And if you have really big signal, it would just overwhelm everything. You wouldn't see this. But this is because it's a little tiny trace signal, and it's coming back and forth from this, okay? You might have experienced things like this. You get a smell in your house or something, you walk by it and you smell it, and you come back and can't smell it. That's because when you went through it, you created enough things that distributed it too much. You had a filament that hit your nose. Okay, so we have this sensor, and we're trying to get this out. There are so many people. There's so much snake oil in these kind of areas. And then fortunately, I helped found this thing called the Institute for Cellular Nanotechnologies at MIT. And we actually had the Commandant of the Marine Corps that I think is based here in Pensacola. So we had a Commandant and come, and I was pitching to him chemical weapon detection. He said, I don't care about that. I want explosives. I said, well, oh, wow, I'm really good at that. I just thought everybody knew. And he said, so he sponsored us for a field trial in Yuma, and this is when Iraq was having all these roadside bombs, and we actually played a pretty big role in eliminating that in the time. But he had us do a field test in Yuma, in the desert of Yuma, which is a lot like Iraq. It's in Arizona, and this is a video from that. So this is the one where we got this sound up a little bit for this one, right? What we have here is we just took one of our devices, we put it on something called the Dragon Runner. And like an 18-year-old Marine is driving this, and he's been looking for explosives along here, and he's going to try and see if he can find explosives. And so you'll hear a clicking sound that's a Geiger counter kind of thing, so you can hear that. And the higher clicking rate means higher signal. So he's going to go slow along this bush because he thinks, that's where you hide explosives under a bush. Promising, but it's windy. It's going away. So this is now it's going to go away, right? So he's like not quite sure exactly where it is. He thinks there's something there. He wants to find it and pinpoint it better. And so now he's very confident. He got it. It's time to celebrate. And then this is like, then he tries to break our device, which I'm listening like, those Marines, you got to make these things tough. So this was using this generation of the device. They now look even smaller than this. This has long been sold as in the company. And what you do is you basically take a little capillary, you fix it with our polymer on the inside, and you suck air through it, and you radiate it with light, and the light tends to waveguide down this to a detector, and you just look for changes in this. And if you have any of the municipalities that have explosive detectors on robots and things, this is the iRobot package. They're equipped now with our explosive detectors, so it's used a lot in homeland security. And this is stuff we invented, more than 25 years ago. It's still the most sensitive explosive detector out there. For a while, we were in all the airports, all the international airports, but TSA got tired of paying our consumables, and they went away from that. But this is Washington National Airport, where they're using one of our sensors. And, it's also kind of cool. They work underwater. Here's a case. This was done out off of San Diego. There's an explosive ordnance simulated. This is an underwater unmanned vehicle, and here in the light you're seeing the GPS traces, and this is it's homing in on, again, a convective current that is transferring the explosives there. Okay, so this is kind of old stuff. I want to come into something late that's really in the news right now that we're also working on. It's PFAS detection, perfluoro and polyfluoroaromatics. These are things that everybody in this room has these in your body. Don't worry, they're not going to kill you, but it's a real concern for the future and what it can do in children. And they were used in a lot of manufacturing. So right now, the EPA has made a mandate that we have to bring these down in drinking water to 4 parts per trillion. There's lots of cleanup going on. They're coming out of landfills. They're coming out of Air Force bases. They practice firefighting. I guarantee you Pensacola has PFAS problems. Okay, so how do we take this scheme that I showed you before, and now I make this, rather than kind of a black hole, I'm going to make it have a new emission here. And so what we did is we made polymers that we put into these thin films, and this polymer has this nitrogen here, this pyridine. This is electron poor and this electron rich. So when you excite this with light, it tends to transfer electrons from this side to that side. It makes a dipole here. And that's a smaller dipole, but if I absorb PFAS into this, the PFAS tends to have a proton that will make this nitrogen positively charged. So this becomes more favorable to basically kick the charge this direction. You get a very strong thing. So this is blue fluorescent, and this becomes green. And so we have done this on different films, on different forms. This is on a particle form and showing you how this works. And so here, without PFAS, you have, this is blue. This is just the fluorescence, or the emitted light that comes out of this. Okay, and you have it blue. It looks like it's glowing blue, right? And at very low concentration. And then as you increase the PFAS in this water, this one comes up and it turns to green, and here's somewhere in between. So here you're seeing that we can see 500 part per trillion detection just with your eyeball in this. And the fact we have these two signals, that actually we can use the ratio of them, it actually gives you internal quantitation. Right? So this is something that you can get quantitative data out of these things. And we've now transitioned this to a startup called Fluoridics. And they have, because they sit there and iterate and do. And so they've now, in my group, we were down at about 10 part per trillion. They're down 100 times lower than us right now. And the different prototypes and devices they've made in this, and that is well below the EPA limit. So this is getting to where it's hard to find things that don't have 0.1. And I can tell you that the biggest challenge in this company is to try and keep clean stuff so we can know when our baselines are right now. Okay, so I used a similar slide like this earlier today. I've been kind of motivated by different people. Al McDermott was a big part of my life. He was a really wonderful person. Very wacky, but a really wonderful person. And hopefully I've shown you how you can do things from a chemistry standpoint to impact sensors. I've been fortunate to have our PFAS was funded by a company. I didn't get around to showing the ExxonMobil. There we're working on hydrogen detection for energy. It's very dangerous, and Department of Defense and NSF had funded us over the years. And this is a picture of my research group in the Great Dome at MIT. I have really great people that work with me. Every year we have a kind of a formal dinner. I usually take them out to a restaurant, but I was really, this last year, the economics pinched me, and it's kind of funny. I told them, I said, I can't do the restaurant party this year. I just don't have the money. And they said, don't worry, we already figured it out. We're going to do a potluck. So they transformed one of our little rooms into like, I don't know how they decorated it. It made it look like the fanciest restaurant. And mainly the women in the front did this. And a few of the guys helped, but it was like, I got some real power women in my group. And it was a really, really nice dinner we had. And this is the night that we had that dinner last June. Okay, so with that, I thank you for all coming, and I'm happy to answer any questions.
Please join me in thanking.
Okay.
All right, questions? This might be the first time I've ever been here and there's been no questions.
There's one there, yeah.
Can you give me an idea of this commercial product that you have and where it's being installed, like a TIA, a TSA, or
Yeah, so the
crowd control?
no, it's not. It's more. It's for the explosive detection, and the company. So I haven't actually. So we had a startup company that produced it originally, and we did some things that went public, but then it was bought by Fluor Systems, which is now part of Teledyne. Fluor's been bought. So it's now part of a major conglomerate, but it's called FIDO. It's mainly used by Homeland Security cities. And the military, they use it. The military uses these very, very actively. I'll guarantee there are some in the area down here, but it's a little too expensive, I think, for consumers. But I'm not sure we need it. But the TSA, we had a product in airports for about 7 years, but the TSA discontinued it because they didn't like our expenses.
Can it be helped in battlefield detection?
Yes. We started out around landmines, and then we got where we really got adoption was that the Army was really beyond their wits end. And when we first went into Iraq, we invaded Iraq. When we were trying to do it, there were lots of roadside bombs that were going off and killing people. It was to detect those, and that's where we got and. They used it that it actually played a very major role in being able to detect those, find bomb makers, do things. So they used it very widely in Iraq, and that helped put away the IED, or the improvised explosive device problem. So it did play a role there. Yeah. Yes?
Hey again. Is it specific to nitrogen-based explosives, or would it be able to detect something such as a TATP?
Yeah. We have done both. We've done every kind of explosive, yes. But the TATP, even that was a peroxide. Even our other one in the box that would do TATP, they tend to give off some peroxides. But yes, it does that, as well as like PETN, and then also ammonium nitrate. We're not that good on, but that's not very volatile in. But yes. Over there. Oh.
You currently have devices in the food industry that have to be used.
You know, the ethylene one is a little bit in a stasis right now. I'm not real happy with the CEO. He thought the market wasn't big enough, and he discontinued the product, which is driving me. I'm like, what? I want to get back and redo that one. I've got to find a sponsor for it. We do, most of the PFAS you get is from your food. It's not from your water. It's not from your food. Plants concentrate it, right? The plants and animals concentrate PFAS. So that's something to bear in mind. So Europe has some regulation around this. The United States has not. It's kind of interesting. We're ahead of Europe in the water. They're ahead of us in the food. But I think there is, we actually are planning to get in the food. Food is very tough because the PFAS tends to stick to it. It's really hard to get it out, to quantify it. It's a challenge. But also in food, we have another company that does bacterial detection. Didn't talk about that, but we can. But we do. I am pretty focused on food these days. Really, I love food. Who doesn't?
Brandon.
You're using carbon nanotubes to bridge your electrodes together. You know, free volume changes and thermal expansion as it gets hotter,
Oh,
and you spread out the distance between them. Do you have significant changes if you're in cold temperatures versus hot temperatures?
Yeah, no, that's a good point. Yeah, temperature, you can always, the good thing is you can usually put calibration curves for that if you want. But one of the things that you bring up is like the nanotubes, like expansion or move. So that little thing, like if they move just a little bit, that changes the resistance dramatically, right? And so that's a big part of what we call drift or if they just, over time they kind of like move a little bit, like we call it creep, right? They creep a little bit. And so what we tend to do right now, and I didn't go into this, but we tend to, when we wrap them, particularly with things like polyfluorovinyl purity, which I think you said you worked on at once upon a time, you do that, you can basically staple them down to the surface. And I always call it my Frankenstein kind of thing. So I always think of Frankenstein on the operating table. They have these things strapping him down. So I have these nanotubes strapped down so they can't move. And that's one of the ways to get away from things like that that are going to give you spurious results that don't make any sense. So not perfect just yet, but that's one of the things about it. I mean, one of the reasons semiconductor electronics work so well is they're encased in glass. Nothing moves, right? And so we have to have things exposed, and it's an inherent challenge, but we're doing the best we can through the stapling.
Any other questions?
Oh, there's
sorry.
one. Oh. There's one. Oh, no.
Actually, while you're walking, I'll let her use
Okay,
mine.
okay, great. Sorry, didn't get your.
I don't have as smart of a question.
Okay, that's okay because I'm not smart. We know that.
But just something that I picked up on while you were talking. With the roadside detection for explosives, do Geiger counters count more than just radioactivity, or can they detect other things as well?
Yeah. So the Geiger counter sound I showed was just an audio. Mm-hmm. So it turns out that when they use these things, if you're looking for stuff, it's better if they're looking at a dial. They're not paying attention to what they're doing, right? So what you want is the Geiger counter. So this was something that I hadn't thought about until the time. This is the only way this works. Is you have to use it through that mechanism. But yeah, we've detected other. We developed things for chemical warfare agents, things over the years. We've done a lot of national security type systems. Oh, my battery went dead? Okay, sorry. I'm back online here. Okay, but yeah, but we've done radiological ones. We're there for, actually one of the ways that you make strawberries and things like that last longer is you irradiate them with gamma rays. And it doesn't cause any chemistry, but it kills all the bacteria. And so we were looking at gamma, and also the same thing even with if you get tissue implants, a lot of times in dentistry, they use cadaver tip tissue, actually, but you want to sterilize that before you put it in somebody. Yeah, it's not a pleasant thing to think about, but there's some applications we've come up with to have radiological sensors that give you kind of threshold that you've sterilized something.
My question is about dynamic range. Do these sensors have a very, being able to measure from differences of very small quantities to differences that are very large quantities in the same sensor? And I got kind of something that goes with that. And how many times can these recover after they've been exposed to the whatever chemical they're detecting?
Okay, yeah, some very technical questions here. That's good. So the dynamic range is always going to be, things will become nonlinear, and at really high concentration they might saturate, and sometimes you find when you get things at really high concentration it takes them forever to reset, right? So there's always dynamic ranges. We tend to focus really on trace detections. We're usually at the very low range, but if you give something a really big dose of something, it may not recover, or it may take a long time to recover. With that, it depends on the different things. We've made some sensors that we've tested over very long periods of time, the electrical ones, The optical sensors with fluorescence, they tend to bleach in about 8 hours. After 8 hours of use, they don't really work anymore. Just intrinsically, things with light and air, and you're creating singlet oxygen and different things like that, it tends to react. And so they're about 8 hours for those, but they are reversible. I mean, I didn't show any plots. I showed you a little bit, but it's very reversible in real time, but it will fatigue if you have it continuously running.
All right. Please join me again in thanking Dr. Scott.
Great question. Thank you.